All right, so let's continue looking at section 4.2. So yesterday, this is what we did. Okay, all the graphs that we did, the degree of the top was less than or equal to the bottom. And we saw a certain kind of graphs we usually get. Sometimes it's separated into three sections. We get those two L shapes with that curve in the middle. Sometimes they can look a little different, but that three-sectioned one, that one's pretty common. All right, today we're going to look at rational functions again. Okay, so we're going to do the same thing we did yesterday. The only difference is the degree of the top is going to be bigger than the bottom. All right. So any questions about the difference between what we did yesterday and what we're going to do today? It's almost the same thing. All right. So one thing that happens when the degree of the numerator is bigger than the denominator, we have this thing called an end behavior asymptote. Okay, this doesn't exist with the kind of problems we did yesterday. But with the ones we do today, it does. All right, so let's suppose we have a rational function, okay, where we have a polynomial in the top and a polynomial in the bottom. So you could have something like 3x squared plus 2x minus 7 in the top divided by x minus 4 in the bottom. Okay, just two polynomials. Well, when we divide them, you always get a quotient and you get a remainder. And we've talked about how we can write that out the long way. Okay, just like if let me show you an example with numbers. Let's say I did 3 divided into, let's say 14. Okay, 3 goes into 14 how many times?
4.
4 times. And I get a remainder of 2. Okay, so one way you can write your answer is your quotient, 4, plus your remainder, 2, divided by your denominator, which in this case, it was 14 divided by 3. All right, so when you first start learning long division, you might write the answer that way, 4 remainder 2, or you can write it as quotient plus your remainder over your divisor. 14 divided by 3, that's 4 2/3. Okay. Exactly the same idea with polynomials. When you divide them, you can take your quotient plus your remainder over your divisor. Well, the only thing that we care about is the quotient. If you can find the quotient when you do division, that's the end behavior asymptote. So really, we're not doing anything new. We're using division, either synthetic or long division. We already know how to do. We're writing down the quotient, and we're stopping. We don't need the remainder for this. Okay, so your quotient is called the end behavior asymptote, which I'll abbreviate EBA. Okay, so any questions on what the end behavior asymptote is? Just the quotient when you do long division. That's it.
So when you go to get your end behavior model, and if you get a quotient with a remainder.
Careful, end behavior model.
Yeah, because I don't understand how you're getting these.
Okay, so end behavior model, that goes back to what we did yesterday. That's when you take the highest degree term in the numerator and divide by the highest degree term in the denominator.
Yeah.
So that's a little bit different concept. This is when you do long division. Okay?
So the problem's already going to be set up to do division?
Yep, it'll be set up just like this. You'll have a polynomial in the top and one in the bottom, and you're going to do out the long division. All right, end behavior model I think is a little easier because you don't have to do division. All you have to do is the biggest degree term in the top, in the bottom, it's faster. This takes a little longer because you have to do division.
You have to do synthetic.
Yep, you can use synthetic division, sure.
Would synthetic division always work, or is it just like, is always one that works better?
Synthetic division works as long as the denominator is x plus or minus, and then you have a number. Okay?
So if there's anything bigger than that, you can't do it?
Yeah, yep. Synthetic, same rules we've always used for synthetic division. It has to be x plus or minus a number. X plus 2, x minus 4. Okay, that's when you can use synthetic.
Are you going to show us examples of both synthetic and long division?
Yeah, I think we'll do one of both.
Just to double check, so if the bottom was x minus 3, then you divide by positive 3.
Yes, it's the number, if you're doing synthetic, it's the number after the minus sign.
Okay.
Yeah. So let's find the quotient, remainder, and end behavior asymptote of this. Well, if you can find the quotient is the end behavior asymptote. They're the same thing. Okay, is this one I could do synthetic division on? Yep, and what number would I put outside? 2. What comes after the minus sign? And what would my numbers on the inside be? Yep, Cheryl?
2 minus 4, 0, and 3.
Good. So she remembered that. 0, we've got to put that in as well. All right, so bring down our 2. 2 times 2 is 4. Add those up, we get 0. 2 times 0. Add those up. 2 times 0. Yeah, 0. Add those up, and we get 3. All right, so let's start with the quotient. Okay, what's my quotient here? 2x squared. You could put plus 0x plus 0 if you wanted, but if it's 0, we usually don't write it. Okay, so that's my quotient. That's also my end behavior asymptote. They're the same thing.
Does that have anything to do with the synthetic division that you just did? How do those connect?
How did I?
Yeah.
Well, this 2, that's from the synthetic division. That's what I got for my answer when I did synthetic division. And then my remainder, that's also from synthetic division. What's my remainder here? 3. Okay. That's it. So that's my end behavior asymptote, and that's my remainder. Now, if you don't want to do synthetic division, if that's confusing, do long division. You don't have to use synthetic. Yeah?
So if you were to write out the quotient with the remainder, would it be 2x squared plus 3x over x minus 2?
3. The remainder is just a number, but plus 3 over x minus 2. Yep. So another way you could write this out is 2x squared plus remainder over original denominator. Again, that's your end behavior asymptote. And this part is your remainder. I would probably just write it that way. Quotient, remainder. You don't have to write it this way, but I would accept this. Okay, any other questions on this one? All right, so we'll come back to this problem. We're going to try to sketch this one, and we're going to use the end behavior asymptote. But first, just want to make a few important points between end behavior asymptote and end behavior model. Okay, so there is a difference between the two. End behavior model, that's what I just explained to Cameron. So when you take the highest degree term in the top and divide by the highest degree term in the bottom. End behavior asymptote, that's your quotient when you do long division or synthetic division. Okay, sometimes the end behavior model and end behavior asymptote could be the same. Sometimes they're different. Right? As long as you know how to find each one. Doesn't really matter if they're the same or different. I'm never going to ask you that question. Right? I just want you to understand the difference in how you find them. Any question on the difference in the steps to finding the EBM or EBA? Okay, and it'll be very clear on a test which one I want. I'd never ask you a question saying, find the end behavior. That's vague. End behavior model or end behavior asymptote. I'll specify which one. Okay, in the kind of problems we did yesterday, okay, where the degree of the numerator was always less than or equal to the degree of the denominator, we had asymptotes that were always straight lines. Okay, they were horizontal. Okay, we had those horizontal ones. We also had vertical ones, but right now I'm just talking about horizontal. Well, what happens if that's not true? Okay, if the degree of the numerator is not less than or equal to the denominator, we can get an asymptote that's curved. Right? So in other words, here's an asymptote, and maybe we have a graph that does something like this. It has a shape to it, and it gets closer and closer to this curved line. And maybe it does it on each side. Maybe we have something that kind of curves and it just hugs that asymptote. All right, so that would give us some really weird looking kinds of graphs. Right? The asymptotes don't have to be straight lines. Okay, and we'll do one where it's not. Right? So what I'm going to do is I'm going to graph the original problem we had, and I'm going to graph our end behavior asymptote, and I'm going to show you that this is correct. I'm going to show you that 2x squared is the correct end behavior asymptote. All right, so let's graph 2x cubed minus 4x squared plus 3. 2x cubed minus 4x squared plus 3. And divide by x minus 2. Okay, so I already have it typed in. In y2, I'm going to graph just the EBA, 2x squared. And I'll start with zoom 6. Okay, and I'm going to have to zoom out a little higher. Let's go up to 30 on the y-max. All right, so what's in red is an asymptote. What's in blue is the graph. Let me make it a little bigger. Can everybody see how the graph in blue is getting closer and closer to the graph in red on each side? Any question on that? Yeah.
Are these calculators supposed to be able to do this?
Yeah. Yep.
I'm only getting half of that asymptote.
Do you adjust your window?
Yeah, I have it. It's regular except for you go up 30 to 30, right?
Yeah, you know what? I didn't even do negative 30. I just did negative 10 to 30.
Negative 10 to 30 is what I
Yeah.
only came up with half of that asymptote.
All right. Sometimes what the older calculators might do, if you want to try one of mine, if I take detect asymptotes off,
Yeah, that's how it came up.
all right, it's connecting it. All right, that should not be connected. All right, and that's just because the older calculators can't deal with it being disconnected. All right, so if you want to try it on a newer one, you can, and it should look like that. All right. So,
What are you putting in parentheses here?
what do I put in? I just put the numerator and the denominator.
Should that make a difference or not?
Let's see. Let's see what happens if you take your parentheses out. I would say it makes a difference.
That's what I'm getting.
Yeah. Yep. So it makes Didn't seem to affect that part on the right as much. It did a little bit. The part on the left got really messed up. All right, so always make sure you use those parentheses. All right, so we can see what's happening here. This graph in blue, as we head to the left, it's getting closer and closer and closer to the red. And same thing on the right. It kind of takes this turn, it comes down, and then the blue and the red get closer and closer. All right, so we have a curved asymptote. All right, so example 6, we just did that. Use a graphing calculator to support the idea that we think that's the asymptote. Okay, and now let's try to sketch it. All right, so to sketch one of these by hand, it's a little harder just kind of artistically because you got to draw a curve. Okay, you can't use like a ruler and draw a straight asymptote. So we think there's an asymptote at 2x squared. We checked it. There actually is. So that's the first thing I'm going to do. I'm going to graph this asymptote. Okay. To graph it, let's just pick a few values for x and then find out what y is. Okay. If I plug 0 in for x, what do I get for y?
0.
0? Let's try, how about 1? 1 squared is 1 times 2. And negative 1? What's negative 1 squared? 1 times 2? 2. All right, let's see. We got that. Can we fit 3? Yeah. 3 and negative 3 are both 18. Yeah, I'm just doing that so I can get an idea of what my parabola looks like to sketch it. I'm going to draw it as a solid line, but then I can change it to dotted after. So I've got 1, 2. Notice here, I'm going by 2's on my y-axis, otherwise I would run out of space. Okay. Negative 1, 2. 3, we're up at 18. Negative 3, up at 18. Okay, so draw your parabola. Okay, and that's our asymptote. All right, what else can we find? Okay, we're not going to have a horizontal asymptote. Okay, this curve is taking the place of that because the degree of the top is bigger than the bottom. But I will have a vertical asymptote. Where's my vertical asymptote going to be? Nick? Yeah, where's my vertical asymptote going to be? Think about how you'd find the domain. It has to do with that. What's the only thing you're not allowed to do in a rational function?
Make the denominator 0.
Yeah, we just don't want to make the denominator 0. And if you can find a value that does, that's usually a vertical asymptote.
So
2. Right, so x equals 2. That's my vertical asymptote. Okay, in these kind of graphs, vertical asymptotes don't go away. You still have them, just like yesterday. What does go away is the horizontal asymptotes. Okay, but you still have the vertical. Okay, let's put that in. All right, now what I'll do is just check some points on my table. I'll check a point to the left of that, to the right, and try to get the behavior. Okay, usually what happens with these kind of graphs is you have a very skinny section that part of the graph gets trapped in. And then on the other side, it's a little bit more wide open. Okay, we've got some other wide open over here. But we've got this very skinny section between the black dotted line and that green dotted line. Okay, and that's what I'm going to play with right now and try to figure out.
Do we not have horizontal asymptotes now? or-
Nope. In this kind of graph, you cannot have a horizontal asymptote. The curve takes the place of that. Still have the verticals. All right, so we got a vertical at 2. Let's check 1.99. Okay, and remember, we're focusing on y1. Forget about y2. That's just my parabola. Okay, so at y1, down at negative infinity. Okay, so way down there. Okay, let's check 2.01. Okay, positive infinity, as high as we can go. Okay, let's check 2.5. Okay, maybe I can find one other point in that skinny section. 2.5 is at 18.5, so almost at the top of my graph. Okay, that's as good as I'm going to be able to do for that section. Okay. The curve I'm about to draw has to get closer and closer to each dotted line. So it's going to look something like this. Okay, I'm trapped in that little section. Okay, now on the other side, it has to come up, staying very close to that green line. But at some point, it has to turn and start getting closer to that dotted line. All right, so let's get a couple points here. Let's try 1. Okay, 1, negative 1. So 1. Remember, my y-axis goes by 2, so that's 1, negative 1. Let's try negative 2. Okay, we're up at 7.25. Negative 2. Let's see. So we'd be up, it's hard to get it exact, but somewhere, just a little bit above 6. All right, and I think that's probably as good as we can get. All right, so it comes up from the bottom. It's going to go through that point. And then get closer and closer to that asymptote. Okay, and that's our graph. All right, so these graphs require a little bit more kind of playing around with it to get the picture. Okay, but you'd never have anything more complicated than this. Right? Also, notice the difference. What's the degree in the top? Degree in the bottom? What's the difference between 3 and 1? 2. You get a parabola, degree 2 asymptote. What if the degree in the top was 5 and the degree in the bottom was 2? What's the difference between 5 and 2? 3. You'd get a degree 3 asymptote. Yes. All right. So if you look at the difference between the number in the top and bottom, that tells you the degree of your asymptote. Okay. The further apart they are, the harder it is to sketch because it starts getting more and more complex. Okay. But you'd never have one more than 2 apart.
So the thing on that picture of the graph, there's only half of it on the small.
How come?
There's only like half of the parabola.
Well, remember, so this is basically our parabola right here, right? That's our asymptote. What's happening is very close to the asymptote. It wants to make a parabola, but it can't because it would divide by 0 if it did. So when it starts getting close to 2, the graph goes crazy. It doesn't know what to do. It starts getting really close. It tries, and it says, wait a minute. If I hit 2, I'm going to divide by 0. So it just says, I'll go to negative infinity. Okay? Same thing here. On the other side, it wants to come in and make a parabola, but it can't, because if it hits 2, it's going to divide by 0. And anytime you divide by 0, it causes that infinity.
Kind of like that hole.
Yeah, it's like we have a gap there. Yep. A big gap. All right, so let's try to sketch this one. Okay, can we use synthetic division to find the end behavior asymptote? No. Okay, the bottom is not x plus or minus a number. Okay, so you have to use long division. What's the difference between Degree 3 and degree 2?
One.
1. So this is going to be a simpler asymptote than the last one. Degree 2 is a parabola. Degree 1, well, let's see what that looks like. Any thoughts what it'll be?
No.
Yeah? No?
7.
What?
7.
7? Oh, I'm thinking more of a shape.
A U.
A U? It's going to be simpler than a parabola. It's going to be one step. It's going to be a line. Okay, but wait a minute. I thought he said there's no horizontal lines.
Just like that, kind of like a little squiggle.
It's going to be a diagonal line. Okay, so it's going to be a line. It's just not going to be horizontal. It's going to be tilted. Okay, which is a little bit easier than the last one. All right, to find out what that line is, let's do our long division. Okay, and you know what? Let's just move our graph down. Put it there. All right. Actually, one thing I should fill in here. Let's put the 0x term. All right. What's 2x cubed divided by x squared? 2x. Multiply it back out. You get 2x cubed. 4x squared minus 6x. And subtract. 2x cubed minus 2x cubed, that's gone. What's 7x squared? Take away 4x squared. 3x squared. And 0 minus 6
Minus 6x plus 6x.
plus 6x. It's not even going to matter in a second. You'll see why. And now my last step. What's 3x squared divided by x squared?
Yeah, 3x.
X squareds cancel. Now, I'm done. That's my quotient. If I wanted my remainder, then I'd have to multiply it out and subtract. But I don't need to keep going.
How do you know that's your quotient? Because it's just x plus something.
Yeah, once you get down to a number, there's nothing simpler than a number.
Oh, it's not a big deal.
Yep, so like if you had an x squared term, then an x, then a number,
And then
you're done. Okay? Once you get to a number, there's nothing else to divide. Okay, so that's my quotient, which means it's my what?
EAB.
My what? My EBA. Okay, so this time my end behavior asymptote, it's not a curve. Okay, it's a line with a slope of 2 and a y-intercept at 3. All right, so I'm going to put my y-intercept at 3. I'm going to graph my slope up 2, right 1, and I'm going to draw that line in.
Wait, how do you get that? Just totally from half of it.
How'd we get what? Oh, those points?
Points, yeah.
Oh, so
You
when
just fill in a number for x.
yeah, when you graph a line, okay, start by graphing your y-intercept,
Yeah.
go up 3,
Yeah.
and then your slope is rise over run. So from that point up to
So
right 1.
x is kind of irrelevant for that right there.
You could make a table like we did for the parabola, but I think that's harder. Graphing lines is easier. Yeah, just use your slope and go rise 2, run 1. But if you want to make the table, you could do it that way too. But that's how I usually graph a line. All right, so we got that. What else did they ask us to find? Okay, end behavior asymptote. That's good. Vertical asymptotes. Okay, vertical asymptotes are where what happens? Yeah.
What makes the denominator 0?
Yeah, whatever makes the denominator 0. X squared plus 2x minus 3. Okay, I think, let's see, we can factor that. Okay, and how does that factor? Let's see, we're going to need a 1 and a 3. And what about my signs?
Plus
+3, -1.
Let's see, that's 3x take away 1 is 2. Okay, so we get a vertical asymptote at
1 and
1 and -3. Okay, so what took the place of the horizontal asymptote? The EBA. Okay, you're not going to get a horizontal asymptote here. In these kind of problems, this is the simplest asymptote you can get. It's either going to be a slant or it gets worse. Parabola, but that's as bad as I would give for a problem for you guys. All right, but there are no horizontal asymptotes. All right, so we got 1 and -3.
Is that because you need the NBA model to find your horizontal asymptote?
Right, which we wouldn't have here. Yeah. So I'll never ask you for an end behavior model for this kind of problem because it doesn't apply. That only applies to horizontal asymptotes. All right, now I've got to just check points on each side and see where my graph is going to be trapped. Okay, it's going to be trapped in some of these sections. Okay? I'm just not sure where yet. Okay, so let's use our table to help us out. Yep.
Is there a quicker way to know which region of the graph it's going to be trapped in?
After you've done a lot of them, you can kind of look at it and have an idea. Like I'm thinking it's going to curve in one of these sections. Okay, possibly come up from the bottom here and then back down, but that's just experience. That's just my guess. And then it might be trapped in one of these sections up here. Yeah, but without practicing and just getting better at it, we'll just have to use our table. Some people can do it in their head too, but I think that's some big numbers here. So 2x cubed plus 7x squared minus 4. Squared minus 4. Okay. Divided by x squared plus 2x minus 3. I mean, think about how much more of a pain this would be without being able to use your table. You'd have to plug in all these numbers we're about to do by hand and do this out. All right, so -1, 2, 3. What's a number very close to -3?
0.99.
Yep, that'll work. Okay, draw a dot as low as you can go at -2.99. Okay, another number very close to -3. 0.01. Draw a dot as high as you can go. Sorry, what's on the other side? Okay, so. All right, let's check 0.99. My guess is that's going to be as low as you can go. Yep. So that's way down here. And let's check on the other side, 1.01. That's as high as you can go. All right, so I have an idea of what's kind of happening here. If you want to get a couple more points, maybe if you're not sure, try -5. Okay, see where you end up. -6.5. So we got 5, 6.5, somewhere down in there. Yeah. All right, so this part is going to come down. It's going to curve and get closer and closer. On this part, we're going to be trapped in this little section here. That seems to happen a lot. You get trapped in these little sections. Okay, and then in the middle. Well, all I have right now is a dot here and a dot here. Let's try 0. Okay, see what we get. 1.3. Right, so I'm going to have to connect all those dots. So it's going to have to go something like that. Okay, so we've got those 3 sections to the graph. Let's see how we did. Okay, that's the section on the left. There's the middle section. And the right section, we're just seeing the tip of it. But that's what it should look like. Yeah, we did pretty good. Hey, so any question on that one?
So we don't have to worry about the horizontal?
No, you can't have horizontals with these type. Yep. That's only when the degree of the bottom is bigger or equal to the top. Okay, if the top is bigger, forget about horizontal asymptotes. This takes the place of it. Okay, and as I think it was Tommy said, this is called a slant asymptote. Okay, it's at a diagonal. Okay. Yeah.
What are you plugging the like close graph into? Are you just plugging it into the original equation?
Yeah, I type in the original equation into y1, and then I'm typing them in under the table and looking at the y values. Yep. Right, so this is one I would expect to see on the test. It's a little simpler than a parabola asymptote, not as complicated. So you'll probably see something very similar to that on the test. Okay, any question on slant asymptote? Okay, and what's the degree of a slant asymptote? It's degree 1. So anytime the top and bottom are one number off, and the top is the bigger one, you're going to get a slant asymptote. If this was a 5 and this was a 4, slant asymptote. All right, and the last one, we're just going to sketch on the calculator. Bless you. Okay, there's nothing you're going to do by hand for this one. Okay, what kind of asymptote would we expect to see here? A slant. 1 degree off, the top is bigger. So we're going to have a slant, but let's just graph it and see what happens. Okay, so we get 2x to the 4th, 7x cubed, plus 7x squared, plus 2x. Okay, and divide by x cubed minus x plus 50. Okay, so what I'd be looking for on this one is for you to show me the window you used. Okay, because they're asking for a complete graph. Okay, so I'd want to see the window. All right, let's try zoom 6.
Can you move your calculator over?
A little bit. All right, so I definitely can see our slant asymptote somewhere in here. You can see it better, I think, on the left side. You can start to see that slant. Right. Does anything look funny about that graph? Something we might want to check out a little closer? There's something here that it looks like it might be this, but I can't tell with this window.
Wouldn't it go up to like at least 50?
Oh, in the denominator? We can zoom higher if we want. I don't think you're going to see anything else happen. I think you're just going to see more of the same. See, now you can see, well, actually that kind of shows something. You can see here it starts to turn, and now we're getting that horizontal asymptote, which is probably something kind of like that. Okay, so that blue curve is going to get closer and closer to those. But something else in this picture I'm looking at that I think I want to check out a little closer. Yeah?
Is there a break?
If there's a break,
Or that is all, it's all solid parabola?
yeah, I don't think we're going to get a break here. We might have a vertical asymptote, and we definitely have a slant asymptote, but I don't think you're going to worry about a break. There's something else here that looks suspicious to me. Yeah?
The way it's flat, it looks kind of like the axis has more than one.
Yeah, it looks in this section right here. Right? It looks very flat. Okay, so I'm wondering, does that cross the x-axis? Let's set our y min to 1 and -1 and zoom in on that. And let's see if it really is flat. All right, so you know what? Let's set our x's from 2 to -3. Let's zoom in even a little more. All right, that window, I don't think that tells me anything new. It still looks very flat, extremely flat. So let's zoom in even more. Let's, instead of -1 to 1, let's go -0.1 to 0.1. Right, so let's just keep these pictures as we're going along. Right, and I'm going to zoom in again on that section right there. Let's try -0.1 to 0.1. So what are we starting to see about that section we thought was flat?
That ain't flat.
It's not flat at all. All right. In fact, if we go in even a little more, let's try like 0.05 to 0.05. So now we're zoomed in extremely, extremely small. We can see it really isn't flat at all. Okay? We've exaggerated it. This is like looking at something 400 times bigger with a microscope. Okay, we've really exaggerated it, but we can see it actually crosses the x-axis 1, 2, 3, 4 times. All right, so this is a kind of problem if I asked you on a test, how many times does this cross the x-axis? You really got to zoom in to check it out. Okay. Any questions on that? Okay, so that's my only point to that problem. Be careful of things you think are flat. If you zoom in, they might not be. Yep.
Does the problem tell you that though? X to the 4?
Yeah, you might expect, you've got this x to the 4th and this x cubed. You got a lot of stuff going on here. So the chances of something with this many terms being perfectly flat, probably not.
I still feel like it isn't all you have to focus on for that the X to the 4th. And that tells you how many times it's crossed.
Yes, that x to the 4th tells you how many times potentially it could cross, but it doesn't guarantee. Okay? And then we're also dividing by x cubed, so all kinds of crazy things could happen to it. All right? So just make sure you zoom in. All right, so homework tonight, it's on 235. It's 40 to 43, 45 to 47, and 51 and 55. Okay, tomorrow we'll do section 4.3, and that'll be our last section before the test. Okay, and I'll be after school tomorrow if anybody needs extra help.